Okay, welcome. We are on chapter 16. This is the beginning of chapter 16. This is trying to understand how we get electromagnetic waves. This is a classical phenomena, the way that we approach this, from Maxwell's equations. Now, if you remember, from the end of Physics 2, we covered how electric fields could be generated by charges, and we also looked and saw how we could produce a magnetic field from moving charges. So now what we're going to do is we're going to take some of the concepts that we've learned, Gauss's law, Faraday's law of induction, trying to think of Ampere's law, and we're going to see how we can really combine all of them and generate the electromagnetic wave, which our eyes know as light. So here we go. Please advance. So Maxwell didn't come up with all these ideas. Maxwell actually united a number of different ideas. He lived from 1831 to 1879. So, obviously this is the 19th century when quite a bit of work was being done on electricity and magnetism. Again, Maxwell's genius was to take so many different ideas and combine them into four famous equations. Maxwell's contributions beyond, just his equations, which are his namesake, of course, is the concept of the electromagnetic waves being based on these equations. He worked on the kinetic theory of gas, which is not all that related to electricity and magnetism. So he certainly did, very diverse collection of work. We know the kinetic theory of gas, of course, leads to what we know as the ideal gas law. He talked about the nature of Saturn's rings. I think he was the first to propose that they had to be made of individual particles because if they were solid, they would not be able to stay together structurally. He explained color vision. Well, that's related to electromagnetic waves. And of course, this is going back to the electromagnetic theory of light. He came up with the field interpretation of electromagnetic waves connected to his four equations. So what do we know? We know that electric field lines originate from positive charges. If you remember all the diagrams that were being drawn, you might remember, oh, okay, we have a positive charge, and then from that positive charge, we draw all these field lines, and they point away from a positive charge. Oh, I guess I would put it right where my video is, and they point toward a negative charge. Also, we know magnetic field lines always form closed loops. They can never begin or end anywhere. That's why we don't have magnetic monopoles. We don't have north poles without south poles. Otherwise, we could have the beginning of magnetic fields. But of course, magnetic fields always close back on themselves. Faraday's law of induction. We know that a varying magnetic field induces an EMF and therefore produces a current from an electric field. And of course, magnetic fields are also generated by moving charges. We know this because we have electromagnets. Okay, so starting with Gauss's law, there's that positive charge with the electric field lines emanating from it. Gauss's law essentially says the electric flux through any surface, and we have this spherical surface shown, is equal to the amount of charge divided by the permittivity of free space, which is a constant, very important constant. But we'll talk about that later and how that's related to the speed of light. So Gauss's law says you want electric field lines, you need a charge. Okay, they start from a charge which is positive, and they terminate at a charge which is negative. Okay, so we got our electric field going on there. However, magnetic fields, they can't, start or stop at any point in space. So for instance, if I have a surface, again, I'll use this gray sphere that you see right here. I see that every magnetic field line that I have enters and exits that surface. What it's saying is the magnetic flux, if you remember magnetic flux from physics 2, magnetic flux is the field integrated over an area. Magnetic flux must always be 0. That means that if I have a field line coming in right here, which would be equal to a negative flux, that has to be countered by that field leaving that surface, and that's a positive flux. So for every entering field line, I have to have an exiting field line. And really what this tells you is that the magnetic field, although it shows the magnetic field starting from negative infinity and going back to positive infinity, the magnetic field lines have to always close back on themselves. Okay? There's no source of a magnetic field where it starts and stops. It always creates a continuous loop, really. Now, Faraday's law of induction, okay, basically says that you can produce an electric field because what a potential is actually the field represents the. I'm going to use a physics. I'm going to use a calculus 3 term here. The electric field represents the negative gradient of the voltage or the electric potential. So really, we can get an electric field if we just start using a time-varying magnetic flux. And this is the principle behind a generator, right? You've got a magnetic field contained within the generator itself. You have loops of wire which are going to have current induced through them. You turn the generator. This changes the magnetic flux within the generator, within these loops. And suddenly we have electricity. This is the basis for power plants. So Faraday's law of induction says that we can get an electric field, sort of a strange integral sign here, but what it's really saying is we can get an electric field in a closed loop by varying the magnetic field that passes through the surface. Oh, it showed an eraser instead. Let me get back to my tool right here. Zoom doesn't have the best tools in the world, but they're the only tools that I have access to. So now I'm going to draw the magnetic field lines. And if we oscillate these magnetic field lines, we can generate an electric field that's going to wrap around them. So again, here is an oscillating magnetic field. It doesn't have to be oscillating. All it has to be is time varying. And what we get to wrap around it is an electric field, the basis for generator. Ampere's law says that a current generate a magnetic field that wraps around it. So we see this symmetry, right? We see a changing magnetic field, which generates an electric field that wraps around it. We see a moving charge associated with an electric field with a magnetic field that wraps around it. And basically, this is Ampere's law, or Ampere's circular, I can't pronounce this, oh gosh, forget it. It's Ampere's law. And again, the magnetic field wraps around a wire carrying a current, and this is basically an electromagnet. So, everyday objects, generator, electromagnet, all these different laws are going to be put together into 4 different laws. Let me see if I can move this right here. Move this to the top. Maxwell looked at Ampere's law and made a modification here. Said, yeah, okay, I understand the term right here, which is basically the electromagnet. We have a current flowing through a wire. We're going to get a magnetic field that wraps around that flowing current, okay? But he also saw that with a changing electric field, you could induce a magnetic field that would wrap around this. You didn't need necessarily the flow of charge. What you needed was this oscillator and changing electric field, okay? And that would produce this magnetic field that would wrap around the electric field. Okay, so putting this all together, Gauss's law for electric fields starting and stopping at positive and minus charges. Gauss's law for magnetic fields that say we don't have magnetic fields starting and stopping at north and south poles, okay? The magnetic field actually connects back on itself. Faraday's law of induction, that we can induce an electric field from a changing magnetic field, and Ampere-Maxwell's law, which says we can induce a magnetic field from a changing electric field. All these laws are finally put together by Maxwell, and they're basically Maxwell's 4 equations. Now these look a little bit intimidating. Let me just go through them with you to make sure that you're not too intimidated by them. So here is Gauss's law for electric charges. Again, it's just saying that my electric charge generates a electric field which radiates out from the charge. That's all it's saying right there. Okay, it's Gauss's law. The next one says that we don't have magnetic fields which radiate out from magnetic monopoles. Magnetic monopoles don't exist. We have north and south poles, which are dipoles, which cause the field lines to reconnect on themselves. Of course, here we have, okay, a changing magnetic field generating an electric field. This is a way of writing Faraday's law of induction using its integral form. And then finally, we have Ampere's law. Here's the Ampere's law part with Maxwell's addition. You know, the changing electric flux produces a magnetic field. Okay. I don't like the integral form as much because it really makes your brain have to concentrate on what these integrals are actually saying. You know, like right here, this is a surface integral. Okay, closed surface. Sometimes you'll see this written to distinguish it from the circular path. You'll see an S here to indicate that this surface is closed, that the circle in the integral sign says we're integrating across this closed surface, whereas these are integrals on a closed circular path. So, the integrals aren't equivalent here. Here's the way I like to see them in, if you haven't taken Calculus 3, this is going to be a little bit unfamiliar. These are the ways Maxwell's equations really, I think, visually make much more sense. And this sign right here is called the del. Okay, it's a del operator. And the del operator, if we're using Cartesian coordinates, is the derivative of the x direction plus the derivative of the y direction plus the derivative of the z direction, with, oh shoot, why do I always go back and forth with that? With an operator that looks like this. So it's technically a vector. And the way you should view this is more the way that we commonly call these equations. Divergence, okay, sometimes we'll shorten this and say the div of E, it's talking about the divergence of E, and curl, okay? And sometimes you'll see it written this way too. Just get the visual aspect of this. Don't go crazy with the calculus end of this. If you've had calculus 3, you're seeing some of your best applications right here. But here's what it's saying: divergence of E, divergence of B. Okay, the field lines will diverge. The electric field lines will diverge from a electric charge. That's all it's saying. Okay. There is no divergence for the magnetic field, which means that the magnetic field doesn't start at a point and just radiate out from that point. That doesn't exist. Anytime we have a magnetic field, it loops back on itself. Okay. Curl says that to get it to loop back on itself, okay, so for instance, if I want an electric field to wrap around itself, I can have a changing magnetic field. If I want to produce a magnetic field that wraps around, okay, I can either have a current that's going to generate that. That's the principle of electromagnets, even, permanent magnets. We have, electrons going around producing in a classical sense, we have electrons going around producing a current. That's the source of permanent magnetism. But we can also get this magnetic field from a changing electric field. Okay, well, that was a long way to get there. So again, let's visualize this. Once again, electric fields will begin at a positive charge and will terminate at a negative charge. That's what the first Maxwell equation says. Okay? We look at the Maxwell equation, we go, oh my God, that looks so complicated. But that's what it's saying. Get the conceptual aspect of it. Divergence of B, div B, what does that mean? Well, it just means that there's no starting or stopping point for the magnetic field. What I show you here is a magnetic field coming from negative infinity and going to infinity. But really, if we want to visualize a magnetic field, anytime we see a magnetic field line, no, it's not a square. I wish you would give me the tools that I asked for. Magnetic field lines are always in these loops. Okay, they always loop back on themselves. In fact, if I were to draw a permanent magnet, I'll draw a permanent magnet right here. Here's my permanent magnet, and I've got a north pole here, and I've got a south pole here. The magnetic field lines associated with this magnet actually go through the magnet itself, and then they reconnect after going outside. So here's what the magnetic field might look like. I'm doing a really bad job of this, but again, we don't normally see these magnetic field lines, but okay, they do loop back on themselves. Okay, so moving on. These are the really important equations in terms of electromagnetic. I took a long time to get here, didn't I? These are the really important equations with regard to generating electromagnetic waves, okay? The curl of E and the curl of B. And here's why. Okay, I'll start you off here in terms of how an electromagnetic wave is created. If I have a surface wave in a pond, I can create the surface wave by taking a stone and disturbing the surface, displacing the surface. And we see these waves radiate out. I can create an electromagnetic wave by disturbing the electric and magnetic field anywhere in space. And this disturbance propagates out as this electromagnetic wave. So we'll start with a radio wave. How do I generate a radio wave? Well, I generate a radio wave by moving a current up and down an antenna. In fact, there are two antennas really that make the most basic type of radio transmitter. It's called a dipole because one is going positive, one's going negative. But I'm moving charge up and down. I'm creating this current that's going up and down the antenna. And this creates a magnetic field that wraps around it. Okay? So as the current goes up and down, it disturbs the local magnetic field. And that magnetic field wraps around the antenna. Okay? So here is really the beginning of an electromagnetic wave. Okay, moving a current or creating this oscillating dipole that's going to create a magnetic field that's going to wrap around. Okay, let's go on to the next step. We've created our magnetic field. Now this is oscillating. Our magnetic field, which oscillates, it's changing with respect to time, now generates its own electric field. Now that's oscillating. And now the electric field is going to generate another magnetic field. So this is the basis for electromagnetic waves. We use that current to disrupt a local electric and magnetic field. And these electro and magnetic fields just start propagating in the form of a wave at the speed of light from the source. Oops. Okay. So Maxwell comes up with this great idea. Electromagnetic waves, if they're predicted by these equations. In fairness, Maxwell didn't call Maxwell's equations. Maxwell is credited with putting them all together. But really, in terms of the first Maxwell's equation, it's really Gauss's law. In terms of the second Maxwell equation, it's an adaptation of Gauss's law for magnetic fields. The third equation is Ampere's law and an addition done by Maxwell. No, it's Faraday's law. The last equation is Ampere's law plus an addition done by Maxwell. So we get to, okay, we have our theory, okay? Our hypothesis, it hasn't been tested yet. We have our hypothesis that electromagnetic waves are created by, this disturbance, and this should propagate through space. And along comes Heinrich Rudolf Hertz to actually demonstrate this experimentally. Yeah, obviously everybody knew that light was around. I think Young had already demonstrated interference, but Hertz was the first to generate electromagnetic waves through this process. And he showed that radio waves could be reflected, refracted, and diffracted. So we, in his honor, call the unit for frequency, which is 1 over a second, we call that the Hertz. Now, here's how he did it. He created an LC circuit, okay? And again, for those of you who've taken physics 2, you might remember this as having an inductor and a capacitor. And the LC circuit was pretty much like the pendulum, okay? It would swing back and forth in terms of energy. With a pendulum, you have potential energy that becomes kinetic energy, that becomes potential energy, that becomes kinetic energy, okay? LC circuit, same thing. The electrical energy oscillates between the capacitor, okay, and the inductor, and then back to the capacitor. So it's going back and forth, back and forth, back and forth. So with this LC circuit, he created a very, very simple circuit. he created a circuit just with you don't see the battery here. We switch. You turn on the switch, it charges the capacitor, okay? And then the capacitor charges up, but then it discharges and dumps the energy into the inductor. So we have this back and forth of energy, this oscillation back and forth of energy. It's an electronic version of the pendulum. Okay, so this is really important because your capacitor here, which is not a normal capacitor. Most capacitors are these parallel plates. He used these spheres right here that actually generate a spark between them due to the intense magnetic electric field. And this oscillating electric field is then going to generate our electromagnetic waves. So oscillator going back and forth, back and forth, back and forth. The electric field stores energy, then it dumps it into the inductor, where it's stored as magnetic energy, and then it goes back to the capacitor, so back and forth, back and forth. But in the process, it's what's happening at the capacitor which is generating the electromagnetic waves, okay? That oscillating electric field, go back to Maxwell's equations, oscillating electric field will produce a magnetic field, okay? That's Ampere's Maxwell's law. And then from this, we radiate these electromagnetic waves. So he's generating these very crude waves by opening and closing the switch. And the interesting thing is he has, this is the transmitter, but he also has a receiver. Now, this is like the first radio. He can change the frequency at which the receiver likes to oscillate by, I think, changing the capacitance. I think he used a variable capacitor right here. And what he would do is he would tune in the receiver at the right frequency that the transmitter was producing, the same, what we would call impedance, okay? And again, very, very crude. How did he know that he was generating electromagnetic waves? Well, you get a spark between those two spheres. How did he know he was receiving them? Well, his receiver would also generate a spark. Wow, this is beautifully simple because you don't need anything fancy, okay? How did that spark get there? Well, it traveled across the room. This wasn't just an electric field being generated by the first transmitter. It had to be a wave because as he, played around with this device, he showed that he could produce, interference. He could produce diffraction. He could produce all the different properties we expect from a wave. Okay, and what he found is from the interference pattern, he found that you could determine the wavelength. He knew the frequency of the LC circuit. And of course, we know that the speed of any wave is equal to lambda times v. And the number that he got was very, very close to that of c. Okay? It's traveling at the speed of light. So this provided evidence to support Maxwell's theory. And this is the beauty of science. Somebody makes a prediction through just going through existing ideas. That's what Maxwell did. He went through existing ideas, the work of Gauss, the work of Ampere, the work of Faraday. And he puts it all together and comes up with something exciting and new, this idea of electromagnetic waves. And somebody else comes along, Hertz, says, I will prove that you are right. And there's the evidence, okay? Yeah, this is very similar to Copernicus and Galileo. Copernicus said, the planets go around the sun, okay? It wasn't all that much of an original idea, but very, very important. Galileo spent his entire life doing what? Performing experiments to show Copernicus's way. So again, this is really the first radio transmitter and receiver. It's not sending anything. If you'd hooked it up to a speaker, all you'd hear is static. You'd hear the crackling of the discharge. But again, these electromagnetic waves oscillating from the antenna. And again, here is the way that we create electromagnetic waves in the radio spectrum, like Hertz did, but now we can actually send information. And it's an important theme for all the different wavelengths that we're going to study in the electromagnetic spectrum. It's an oscillating dipole, which generates the electromagnetic waves. That's the simplest way of thinking about this, because if we go back to this right here, okay, that capacitor keeps reversing polarity. So those two spheres, top one's positively charged and bottom one's negatively charged, that's a dipole. Then it switches direction as the circuit oscillates. The top of the capacitor is going to be negatively charged. The bottom is going to be positively charged. And it's really the basis for our antennas, which we broadcast. A little more sophisticated. This is what the antenna would look like in its simplest form if it were a dipole. Today, we only stick part of the antenna above ground. The neat thing is they make, you know, the top end, the radio mast that you can actually see for AM, and then the bottom end is grounded, so uses the earth as a part of the antenna. But this reversing of currents that's taking place generates this oscillating electric field, which induces an oscillating magnetic field. And that's basically how you get electromagnetic waves. The electric field produces a magnetic field, the magnetic field produces an electric field, and it's all predicted by Maxwell's equations, okay? The electric field is perpendicular to the magnetic field, okay? And the electric field is perpendicular to the direction that the wave travels. The magnetic field is perpendicular to the direction that the wave travels, okay? So here's a nice little picture. I stole this from Wikipedia. I should have an attribution here, but this is a dipole antenna producing a radio wave. Microwaves are created, you know, sort of in the same way. They use klystrons and magnetrons, which create an oscillating field to generate them. In terms of infrared, one of the easiest ways to create infrared light is to have the bonds between a molecule oscillate, okay? And this oscillate produces an oscillating dipole. And we get to the visible. It is the electron, which is oscillating around the nucleus that's generating the oscillating dipole. Ultraviolet light are the middle to inner electrons. X-rays are the innermost electrons. And then we get to gamma rays. That positive nucleus, as it oscillates, actually produces an oscillating dipole field to produce gamma rays. So, you know, you scale it to you know, smaller and smaller degrees. Radio waves are the easiest to make because we can use big antennas to create them. But as we go to a smaller and smaller level, still an oscillating dipole. And again, here is what our electromagnetic wave would look like. The red shows us the oscillating electric field. The blue shows the oscillating magnetic field. This is a harmonic wave. All waves can be broken down into harmonic wave sines and cosines. So if we're looking at this, the electric field is oscillating up and down. The magnetic field is oscillating in and out of the page. And it's propagating, in this case, in the negative x direction. And again, we call these transverse waves. If you remember, I believe from physics 2, we classify sound waves as longitudinal waves because the oscillation was in the direction of propagation or parallel to the direction of propagation. Transverse waves, the oscillation, the electric field, and the magnetic field are perpendicular to the direction that they're traveling. Okay? Well, that's it for the first section. And again, if you haven't taken, a few of you haven't gone through this in physics 2 yet, the important thing to take in here is Maxwell's equations. Okay, they look very, very complicated, but visually, they're saying very simple things. Okay, it's the curl equations, the last two, that say oscillating electric field produces a magnetic field. Oscillating magnetic field produces an electric field. Did I do that properly? Oscillating electric produces magnetic. Oscillating magnetic produces electric, and it just keeps repeating itself. The electric field produces a magnetic field. The magnetic field produces an electric field. It just keeps propagating through space. Okay. And one of the important things is the electromagnetic waves don't need a medium. They're just self-propagating. Okay. What do I mean by medium? Well, you look at the waves in a pond, the surface waves need water, or they need the interface between water and air. Sound, you can't hear in a vacuum. You need the air molecules. That is the medium. Waves on a string, the string is a medium. Well, this is interesting because here we have a wave that doesn't require anything at all. By the way, there's another type of wave, which we'll talk about with relativity, called a gravitational wave, which also doesn't technically need a medium. The medium is actually space-time. But, you know, if we think about the electric and magnetic field, the medium, if we accept things like, you know, a version of string theory called M theory, these are actually oscillations in 11-dimensional space, but that's a whole other story. Well, in any case, electromagnetic waves, electric waves that oscillate create electric fields that oscillate create magnetic fields that create that oscillate create electric fields.